You have fallen into Event Horizon with John Michael Godier. Dr. Kipping is the Assistant Professor of Astronomy at Columbia University, where he researches extrasolar planets and moons. Dr. Kipping also leads the Cool Worlds Lab at Columbia, which includes a YouTube channel and a website where you can learn about their research. Dr. Kipping's other areas of research interests also include study and characterization of transiting exoplanets, exoplanet atmospheres, Bayesian inference, population statistics, and understanding stellar hosts. He is also the principal investigator of the Hunt for the Exomoons with Kepler HEK project.
Dr. David Kipping, welcome back to the program, which must be now, 7, 8, 9 times?
You know what, John? I think you're my favorite podcast to do. I always really enjoy our conversations.
Well, likewise, I've been watching your podcast as well, the Cool Worlds interviews. Very good stuff and very interesting. But I have to confess that in almost half a century of being interested in science and futurism, very rarely does anybody come up with a really, truly Freeman Dyson level idea. It's very rare. Occasionally it happens, but an idea that just puts a total new spin on, and I mean that word very carefully, spin on speculative technologies and things we could do. And in this case, it's T.A.R.S. And it is the simplicity of the idea is beautiful. Anyone that's ever had a radiometer spinning in the sun on the globe knows what this is. It's very intuitive, and I'm surprised nobody came up with it, frankly. But the idea of tossing a chip level microprobe to another star system inexpensively, among other things that are possible with this idea, just floored me. Congratulations. You officially floored me with an idea. Tell us about T.A.R.S. Lay it out.
Wow, that's extremely high praise coming from you, John, because I know how incredibly well read and how deeply you have thought throughout your writing and many interviews about interstellar travel. So, I really appreciate that comment. T.A.R.S. has been an idea that's been with me for many years. Like so many seeds that, they begin maybe a decade ago and they kind of fester in the back of your mind and you start adding little pieces to it. So the idea, T.A.R.S. stands for Talked Accelerator Using Radiation from the Sun. It's maybe not the best name. So some people have said to me, now whenever I Google, because it's inspired by Interstellar, of course, the movie Interstellar. Whenever I Google T.A.R.S. Interstellar to try and look for this thing, all that comes up is the robot, of course, from Interstellar. So maybe I should have thought of a better name. But I just wanted to do it as a homage to this wonderful film. And the spinning aspect is, of course, a component of that movie. So the basic idea, as you said, is kind of like a radiometer. You have two thin sheets of metal, is kind of the easiest version of this to imagine, and they're attached by a tether. And one side of these sheets is silver, and the other one is dark. And they're in opposite relative phases to each other. So if you were looking at it face on, you'd see a dark side and a silver side. And if you flew back to the opposite end, it would switch over. And so this thing will feel a radiation pressure, just like a solar sail. If it sits out in space, the whole thing wants to move. But of course, the silver side wants to move more because it has twice, it's more reflective, so it will have twice the number of photons, essentially, that are bouncing off and coming off. And so that produces twice the force. And so this is going to have two effects. The first is that the whole thing wants to move outwards, just like a solar sail, which is kind of annoying because the big problem with solar sails is that as they move away from the sun, they recede from the power source, the acceleration decreases, right? Because you're going further and further away from the light source. And eventually, as you get out into the depths of interstellar space, your star becomes a distant speck of light where you can't really get any interesting acceleration of it at all. So that was always a problem that bothered me. And then the other aspect of it that kind of comes in here is the spinning, of course. So if you have this asymmetry in reflectivity, it will feel a torque and it will start to spin. That spinning is a bit like a flywheel that you might have in your car, or that NASA have built some flywheel batteries that are really impressive and can store huge amounts of kinetic energy just by spinning up, spinning up, spinning up. That kinetic energy is stored like a battery. And so this thing too would store up energy. And so the final part of this puzzle to try and solve is to keep it in place and to stop it receding from the sun. And that's where I use this other idea, which I worked on a few years ago, called a quasite. And a quasite is a sub-Keplerian orbit, we would say. So Keplerian orbit means you orbit the sun following Kepler's laws, which basically says that, period squared is proportional to some major axis cubed. That's the law we all learn, maybe upper level high school physics, or at college. If you take astronomy, you'll certainly learn that famous law. And so this quasite, because it's being pushed by the sun, it effectively reduces the force of gravity inwards from the sun, right? Because you've got the force inwards of gravity, which is very strong, but then you've got a force outwards, which isn't as strong as gravity, but it obviously cancels out some of that gravity, essentially. And therefore, the sail, this T.A.R.S device, in its mind, if you like, in its worldview, it's orbiting a star that's half the mass of the sun than it really is. And so it effectively decreases the mass of the sun. And so it will still orbit at whatever symmetric axis you put it at, but it will orbit slower than it should do. Hence the name Sub-Keplerian. And so that's the key. Once you do these two tricks, you put it in a Sub-Keplerian orbit, which you have to do by just sort of injecting it into a 1 AU orbit with the right tangential velocity, essentially. And second, you just let it spin up. And with those two things, you have a battery that will spin up faster and faster and faster. And eventually, there's a couple of things we can talk about. There's the propulsion aspect of it that we can get into. And then there's also the potential of using this as a magnetic field device as well. So there's all sorts of interesting things once you have a huge battery in space like this.
I have a burning question regarding the magnetic field idea.
Let's do it.
So there was, you remember Jim Green, who's retired, but he was the chief scientist of NASA for a long time. And he came up with an idea of placing a magnetic field generator in between Mars and the sun at a proper distance and generating relatively small magnetic field that covered the entire planet just because of distance. Could you do that with T.A.R.S? And say you're using T.A.R.S to generate a magnetic field, could you put it out at a distance like that and cover the whole planet effectively with an artificial magnetic field?
Yeah, there's two aspects to that. One is the quasi-orbit will help you there. So the aspect of the quasi-orbit is that orbits, remember, slower than it should do. So imagine Mercury compared to the Earth. So Mercury orbits every 88 days. And so it often overtakes the Earth in its 365-day orbit. But we could put a quasite at Mercury's orbit if we wanted to. And if we did that, you could engineer exactly how fast you want it to orbit. You could choose that its quasi-orbit was sufficiently slow that the mercurial orbital period was modified to exactly 1 year. So in that case, when we sometimes see like a Mercury transit in front of the sun or a Venus transit in front of the sun, those are very spectacular events, you would have a permanent transit, right? So when you look at the sun, you'd see this thing in front of the sun all the time, and it just happens to live at the same major axis of Mercury. And so that's exactly what you need, of course, I think, in this idea of sort of, long range protection. And then you get the projection effect that the field size would essentially cover up a larger sky projected area as a result of that perspective effect. So that's certainly something you could do with Mars as well. I hadn't actually thought about the specific orbit in that way, but I think that's a good idea. The other aspect, of course, you'd probably need many, right? So an individual T.A.R.S doesn't produce a huge magnetic field. You're probably going to need a huge swarm of these. And maybe I should just backtrack for the audience to explain how this field is generated. When you have a spinning stick in space, essentially like this is, something spinning in space, if you charge one end of it with a positive electrical charge and the other end with a negative electrical charge, you have now a spinning dipole. And spinning dipoles, by Maxwell's 4 laws of electromagnetism, you can show that they must produce a magnetic field. So that's all it really is. It's just a consequence of electromagnetism. It's the same way that, light is an oscillating electric field, and that oscillating electric field produces an oscillating magnetic field that's 90 degrees out of phase with it. And that's what light is. And that magnetic field produces an electric field and it just self-propagates all the way. So in the same way, if we spin electric charge here, it will produce this magnetic field. And so we suggested that, one application would be to put these in orbit of a planet. In my mind, I was thinking of something much more local. I think in the video I made, I talked about putting it in a geostationary Mars orbit. So that would be a pretty wide orbit around Mars, but if you put it far enough away, it would hang out above the same longitude and latitude, essentially above Mars at all times. And then even a fairly small magnetic field would be enough to provide maybe local protection to that spot under the ground, on the ground that you were interested in protecting. So I think the idea of protecting the entire planet, you could certainly make it easier by doing the quasite closer in, but you'd still need a large number of them to get a reasonable magnetic field strength, because each individual one will certainly not be enough to protect a whole planet.
But the beauty of the idea is economy, because this is not a complicated idea ultimately, but you may require some very strong materials. If you're looking to sling a micro probe out, you probably need to make that thing out of graphene or some extremely strong material. But for the magnetic field idea, is that also the case that you would need those types of materials, or could you do it with something cheaper for that purpose? In other words, is there a difference in T.A.R.S between launching a probe versus creating a magnetic field in that regard?
Yeah, the magnetic field is definitely sensitive to how fast you spin the dipole, obviously, and the limit of it not spinning at all, you don't get any magnetic field. So it's sensitive to how fast you spin it, and you want to spin it as fast as you can. And of course, the problem with spinning anything fast in space, again, sort of inspired by Interstellar, but of course, this has also happened in real life. I think the Neil Armstrong, one of his early missions, one of the Mercury probes, I think, had an issue where the spacecraft was spinning very quickly. And so that risks you blacking out, right? Because the force of the rotation creates a centrifugal effect inside the spacecraft. And so the same effect here will produce a huge tension on your tether that's holding this thing together. And eventually that tensile strength will be overwhelmed by the centrifugal force. So in our paper, we kind of chose the best materials we could, and we tried to think about things that actually exist. So we tried to avoid graphene, which is the obvious ultimate material to use in this sense. Although maybe you could go even crazy and say, like, I want to use neutronium or something, but that's really getting very sci-fi. But if you stick to sub-graphene materials, probably the next best thing is carbon nanotube sheets. So you can buy these on Amazon, actually, wildly enough. They're not cheap, so they're $500 or so. You can grab a small sheet of this for yourself to play around with. And they're sort of, we know how to make carbon nanotubes, and these are sort of randomly aligned. So they're not in phase with each other, essentially, in geometrical space. And so they're still very strong, but they're not as strong as they could be if you aligned them all up into a grid, which is essentially kind of what graphene is. So manufacturing large sheets of graphene is beyond us, but for these carbon nanotube sheets, these CNT sheets, you can get up to about 11 kilometers per second or so before the material starts to come apart. So at that kind of speed, that's going to give you the biggest bang for your buck in terms of both interstellar propulsion, but also for the magnetic field. The beauty of the magnetic field, we didn't get into the engineering of this too hard. I think there's lots of interesting engineering challenges with how you'd actually do this. And I want to be very honest about that. This paper was just you very kindly compared the paper to something Freeman Dyson might have thought of. And I would take that, because Dyson, in the same way, didn't worry about necessarily the engineering of a Dyson sphere, how you'd actually manufacture the thing. He was more interested in the principles of what does physics tell us is possible, and what physical principles could you exploit. And so in the same way, we've tried not to get too hung up on the specifics of the engineering blueprints of this thing. But I think there are maybe more work that could be done in that sense. But I'm excited by the possibility that a lot of folks have reached out to me and have come up with ideas. I've had a couple of space companies reach out to me and said, oh, if you want to launch this thing in October, we have a 1U CubeSat slot. I'd love to give you a space. And I've had to respond, like, I don't have anything built yet. This is just a paper, but this is great. This is exactly the effect I was hoping to have, would be to inspire some brilliant engineers out there to maybe try flying some things in the near future, and we could test out just how strong do these fields get, just what kind of how do these materials cope in the vacuum of space under realistic conditions. So there's still a lot to be done in terms of the realism aspect of this.
So size and testing and the idea of CubeSats and things like that, how small can you make the T.A.R.S to do proof of concept stuff?
Yeah, in the paper, the fiducial model we came up with, which we sort of optimized I don't want to use that word too hard, like we soft optimized to for interstellar propulsion purposes. It has kind of a strange shape. Actually, kind of looks more like a kite, like a diamond almost, was the shape that me and Catherine Lampo, who is the engineering undergraduate who helped me with this paper at Columbia. And so we engineered this kind of this optimal design, and the size of that particular design was about, let's see, I think it was like 63 meters by about 12 meters or so, which sounds huge. I mean, that's obviously compare that to James Webb, which is 6.5 meters across. That's obviously much larger than the fuselage of Starship or something, but it doesn't need to fit inside directly because you could of course unfold this thing. It is just a very, very thin sheet of metal. It's only a micron thick, so you could easily roll it up, and the whole thing would only weigh about 1.6 kilograms in that case. So that's attractive because 1.6 kilograms is well within the weight limits of a 1U CubeSat system. And if you did launch a whole fleet of those things, I mean, think about Starship. It can launch 100 tons, I think they're talking about. So if it eventually works, so 100 tons, you could launch thousands and thousands of TARS. So you could really have a lot of fun covering Mars with magnetic fields in that case. So I think that's the attraction of it, is that it is a very simple system. It's just a sheet of metal that you roll up and stick inside a space vehicle. I think the two most challenging aspects for, if we're going to try and build this now today, like what's, for a test, what's the next steps? And I've been actually speaking to some undergraduates at Columbia to try and build a small team here that maybe we could build a test bed. And I think the two immediate challenges are the deployment of that system. So yes, you've got it rolled up, but how do you unfurl it safely and get it into the position you want it to be in? Do you use maybe probably most realistically, you use some kind of micro thrusters, probably even water jet thrusters, actually might be the cheapest and easiest way to do that. And then once you've got it up to speed, you can sort of detach those thrusters. And then the thing should be self-sustaining. And then you need telemetry off it as well. But getting it up to some initial rotation is important. It's kind of like riding a bicycle, right? So when you try and balance on a bike, it's incredibly unstable and it's very difficult to balance on a bike. But once you get it going and you've got some motion, the gyroscope effect gives it more and more stability. And of course, the faster you go, the greater that stability is. And so the same thing here is that once it gets going, it's going to actually be quite difficult to topple it over, and it will just kind of sit there gaining more and more speed until it actually rips itself apart. Or you dissipate that energy through a magnetic field, because that will of course dissipate energy through cyclotron radiation, which is another interesting potential. Like that radiation could maybe be harvested and used for something as well. That's kind of converting solar energy into cyclotron radiation. And so there's all sorts of interesting consequences of just an incredibly simple idea of just a spinning sheet of metal essentially in space.
And that's the beauty of it, though, because in its conceptual form, it's very cheap and very elegant on its face. I mean, once you implement these things, it always gets more complicated. But on its face, it's just extremely simple. It's a radiometer. Now, what defines the odd shape of TARS as you guys laid out in the paper? And there, by the way, for everybody, there will be links to the paper and also David's Cool Worlds channel video on TARS, which explains this visually very, very well. And all of a sudden you're watching it and you're like, oh, I understand. Mm-hmm. But let me ask you that, that question is
about the shape.
Yeah, the shape. What defines that? Because that's definitely an odd shape for space.
Yeah.
For a spacecraft.
Yeah. So when we first came up with this, the easiest example I gave you to begin with was just this tether, right? So a tether, like a thin piece of Kevlar or something, if you like, and then 2 sheets of Mylar just attached to that. That's kind of the simplest version that we could probably trivially launch right now. In fact, that's not a complicated thing to launch. But the problem with that is that the tether is very wasteful, right? So the tether is mass, but it's not really receiving any meaningful amounts of solar radiation. So it's not doing any pushing. So really you want the whole thing as much as possible. Every gram of mass, you really want to be doing something useful in terms of the spin up procedure. Otherwise, it'll still spin up to critical speed, but it will take decades or centuries. Whereas with the optimal design, we do it in less than a year. So actually, even at 1 AU from the sun, it will spin up in 351 days in an Earth orbit to its critical speed. So that's pretty good. That's kind of the speed you want. You can do it even faster than that, actually, with some kind of more eccentric orbits and stuff that maybe we can talk about. But yeah, nominally, you can do it in less than a year. But if you want to make it, to get to that 1 year speed, as I said, you want to use every single gram of mass there. So the first step was just get rid of the tether and make the whole thing a solar sail. Just make it like a rectangular solar sail where you just kind of paint one side of it silver and the other side dark. That would, we call that the ribbon in the paper, like a ribbon of solar material, of solar sail material. And that's okay. But then when you look at the math of it, you realize that's also kind of wasteful because when you have this centrifugal force, the way to think about it is it's like a weight hanging off a string, right? So the two ends of this spinning thing are like pulling, like imagine someone gripping both ends and pulling it really, really hard. And so the greatest tension this thing feels is actually right smack bang in the middle between the two joining parts, the dark and the silver part. That's where you get the greatest tension between in the sheet of material. So you need the most material there, right? Because the more material you have, the stronger it will be. But as you get closer and closer towards the edges, there's less and less stuff below it. I guess it's kind of like thinking about how when you're on the surface of the Earth, you have the entire atmosphere weighing down on you. Whereas when you're on top of Mount Everest and you're close to the end of the atmosphere, you have less atmosphere weighing down on you. And so similarly, as you get close to the end of the T.A.R.S, there's less force pushing against you, and so the tensile strength doesn't need to be as strong. So you end up having to like kind of taper off this system. So we end up with this kind of kite-like shape, and at the very end of that device of this system is where you put your payload. So if you did want to travel to another star system, or even I should say it doesn't have to be another star system. You can do travel to Neptune or Planet 9 or whatever it is, deep space missions in general. You would attach that payload, which we imagine to be a chipsat, similar to what Breakthrough Starshot had in mind. In fact, we were very much inspired by that. It really, the whole concept is inspired by Breakthrough Starshot as much as it is by the movie Interstellar, because they're really trying to push the limits of what can be done. And I was merely asking in this paper, is there a way to do it without the giant laser beams? That's all I'm trying to do. I'm just trying to achieve as close to I can as possible what they're pulling off, but with way less resources. Like, can we just do this now, today, with the existing stuff, rather than having to have a 100 gigawatt laser system on the Earth, which would be incredibly expensive to put together and have all sorts of military concerns and political concerns about building something like that. So yeah, you fire off the end of this tether and it should shoot off at about 11 kilometers per second. Of course, you could do it twice. Both ends could fire off in short succession of one another. And that after that point, the thing will keep spinning, but it will just slowly shed itself from the outside in. As it keeps spinning up and up, progressively you'll rip off more and more pieces off the ends until eventually there's nothing left. So it'll disintegrate, which is not particularly hazardous for the Earth or any other object, because of course this thing was so light. It doesn't really have a huge amount of kinetic energy in absolute sense.
It would just at best produce a slight meteor if it hit Earth. Now solar system exploration using T.A.R.S, does this give us an advantage with existing materials, stuff we can do right now? I'm setting aside graphene over next to the space elevator for the time being, and we'll get to that with interstellar travel and speed. But the question is can we deploy a T.A.R.S with existing materials that would get us to a planet like Uranus faster? With, say, you put up a bunch of them, each with a different instrument suite, microprobes, whatever you can do with the size that you have, and get to a planet like Neptune or Uranus faster than we can do with a chemical rocket, in addition to being cheaper.
Yeah, so the key to this is to combine these two aspects we've spoken about. So we talked about the magnetic field aspect, and we talked about the vanilla version that's just based off the strongest material you can find. And you can actually combine those two aspects together. So if you don't use charges, if you leave this thing uncharged, no magnetic fields, then the fastest you can do is kind of comparable to Voyager 1, Voyager 2 speeds. So great, it's very, very cheap. You could launch, as I said, this thing's 1.6 kilograms. It's just a sheet of metal. You could launch, presumably, a huge swarm, a daisy chain, continuous chain of tiny, tiny microchips that would form almost like a relay system across the entire solar system, right? So you could have huge download speeds potentially, continuous monitoring of the planet you're interested in. So I think in that sense, it could be almost like a new paradigm in terms of the type of information you're getting. But the actual the initial travel speed wouldn't be any faster. But once you've established the daisy chain, then it's essentially speed of light limited, right? Is the rate that you're getting information back. So I think that's sort of a different way of thinking about travel, because normally you're very concerned with the vehicle's speed. But if the thing is so damn cheap, you can just launch essentially infinity number of them, then there's no reason why you couldn't essentially form a live feed. You can have, go to YouTube / Uranus live feed or something, and you could be able to watch a 4K video stream of what's going on in Uranus. That'd be kind of fun. Although a video stream modulo the light time travel effect, of course, but it would be pretty cool to be able to see that. But if you really are obsessed with getting there as fast as possible, just with a one-off shot, then you need to combine the charges in. And so by doing that, the whole idea behind those charges, I mean, we didn't actually think of the magnetic field as a useful thing initially. Initially, it was just a pain in the butt. The reason why we put the plus and the minus charges on the ends was to create an extra amount of strength to the material, essentially. And I was really inspired by thinking about the Earth, because the Earth is spinning very, very fast, and really a piece of rock should fly off. The Earth is spinning at something like, I think it's like 500 kilometers per second or some crazy speed, or maybe 500 kilometers per hour. I'm not sure. There's some crazy number of how fast the Earth is spinning. And so if you think about logically, everyone should fly off. And of course, that's what, flat earthers might say or something. But of course, the reason why that doesn't happen is because there's a restoring force. And that restoring force is gravity. And that gravity kind of comes for free because the Earth is so massive. And so the key was, could we create a restoring force like the Earth enjoys that keeps everything stable on the surface without flying off, with some other force, because we can't use gravity. And so naturally electromagnetism would be the next obvious thing that you'd reach for. And so that was why we put the plus and the minus charges on, was to create this additional strength. And we did an energy balance calculation in the paper where we sort of showed that the absolute maximum you could ever churn this up to would be when all of the solar radiation hitting this thing was essentially being converted into cyclotron radiation. So a magnetic field, a spinning dipole will generate cyclotron radiations that will kind of shoot off the north and the south pole of this thing, a bit like a pulsar or something, or a neutron star, where you get the radiation coming off the poles. This will do the same thing. And so once the amount of incoming radiation equals the amount of outgoing radiation, it can't spin up anymore past that point. And so we calculated that would occur at about 1,000 kilometers per second. So that's sort of the limit of how fast this thing could go. But that's, of course, 2 orders of magnitude. That's 100-fold faster than Voyager 1, Voyager 2 speeds. And so now you're going at, I think, 0.3% the speed of light. So not as fast as Breakthrough Starshot. Starshot's talking about 20% the speed of light, or maybe 10% the speed of light, depending on which version they're messing with. But, we're at 0.3%. So that's still a very long journey to Proxima Centauri. It's still definitely multi-generational. Personally, I'm okay with it because it's something we can do right now, and I'm thinking that personally we should be comfortable with the idea of interstellar travel being a multi-generational activity. The laws of physics seem to demand that that's going to be part and parcel of what we have to do. So I would rather launch something now knowing that's going interstellar, it's at least possible, rather than just assuming one day we'll figure out superfusion drives or something, or warp drives, because who knows? I mean, that might never happen. I'd rather make sure we get something out that can actually reach the stars in a few hundred years than something that will never get there.
But there are other scientific concerns here, because if you're doing something multi-generational, you're still sending probes out into the interstellar medium, of which we only have 2 probes looking into that, and they're going to be dead within a number of years, so Voyager 1 and 2. And I think anything else that is dead that we've sent out there, other than, New Horizons will eventually get there. But the interstellar medium itself is interesting. And I think that's uncharted territory in a way, because sending a spacecraft through that, especially a microprobe, I mean, what happens if you hit piece of dust, something like that, at 0.3% the speed of light?
Yeah.
And with Breakthrough Starshot at 20% the speed of light, that is ridiculously fast. The problem with that idea is it's energy intensive. You need the laser and all those sorts of things. With TARS, you don't.
Yeah.
But what do you expect in, say we send a stream of relaying TARS probes, microprobes, out to Proxima Centauri, whenever it eventually gets there. What can we learn about the interstellar medium using these types of probes? When you've got a bunch of them out there, what can you maybe do to study that in the meantime and gather scientific data above and beyond your eventual goal of getting to Proxima Centauri?
Yeah, that's a great question. It's not something I've spent a huge amount of time thinking about, but I can think of some things you would do. I mean, because you can launch so many of these things, of course, each one could be bespoke for a different instrument. You're probably not going to be able to pack a ton of instruments on these things. The size we imagined in the paper was a 10 centimeter by 10 centimeter payload. So that's about the same as sort of the size of an iPhone or something, right, roughly. So it's something that you'd be able to pack all of the technology that you'd get in a modern smartphone of that kind of level of granularity. So you could maybe have magnetometers, you could have accelerometers, gyroscopes, you could have camera systems, electric field monitoring. Maybe it'd be difficult to do sample collection on board such a thing because the idea would be you don't really want to be impacting anything. And in fact, to come back to this moment you mentioned about the breakthrough starshot hitting material, and potentially that would be catastrophic for the sail. An advantage I think we have is not only the fact we are moving slower, of course, which is somewhat of an advantage for not being destroyed by interstellar dust, but it's also an advantage that we are not a sail, right? So the sail, like the energy of getting this thing up happens at 1 AU. And so you're doing all your spin up in a kind of controlled environment. And once it flies off into interstellar space, it's tiny. It's no longer really a sail. It is a tiny microchip. It's only 10 centimeters by 10 centimeters. Whereas Starshot have the nominal design, I think, is a 3-meter size sail, maybe even a bit larger than that. Maybe it's 10 meters. So that obviously just by sheer aerial size, it's much more likely to have an impact than we are. And of course, it's that whole system is extremely light, whereas our payload doesn't necessarily have to be low aerial density, we'd say. So the actual mass per unit area ideally isn't too high, but as I said, it could be comparable to a thin sheet of sort of silicon, like a motherboard essentially. So it could have a bit more density to it to sustain impacts. So I'm a little bit more hopeful about that. Some folks have been commenting to me, well, you could launch a TARS could launch a TARS, right? You could have sort of the magnetic field protection aspect being launched off. I'm struggling to see exactly how that would work personally, but it is interesting to think about. There are ways of using magnetic fields to protect us against interstellar debris as well as we travel. But to come back to your question about traveling into the interstellar medium, we obviously don't know very much about the interstellar medium. There are a few probes. It's not just Voyager 1, Voyager 2, New Horizons. There's also Pioneer 10 and 11, I think, which are also moving interstellar speeds. So we'll eventually cross the heliopause as well. And so we have some very limited information from those probes. And there's so much we don't know. I mean, obviously, as the search for Planet 9 has been highlighting, we don't even know if there's a 10 Earth mass planet out there. That's completely possible. There's something that's just been evading all of our telescope observations, and that there certainly seems likely to be Oort cloud or just trillions and trillions of pieces of ice and cometary material, maybe minor planets, and those are important, of course, for potential fuel stops for future interstellar missions as well. Right? We want to know where are the pit stops that we'd be able to get that H2O that we could then split into hydrogen and oxygen for a future mission. So that's the kind of aspect that I get most excited about, is actually finding places, mini worlds that we could potentially visit one day.
Well, that's the big question, isn't it? Now that we have the Vera Rubin Observatory online and already doing science, which it basically, I think it's at least a contender for having stealth discovered 3i Atlas.
Yeah.
Because it saw it first, just it wasn't recognized because they're testing the telescope. But the initial testing is already useful, and it's really going to usher in an amazing telescope. The thing is, it's going to spot Kuiper Belt objects that we didn't know were there. And there was recently a discovery that actually created a little bit of a problem for Planet 9 of a new Kuiper Belt object. And there are questions, because it's not just Planet 9 or Planet 10, or however you want to number them based on your feelings on Pluto.
Yeah.
But the thing is that isn't the upper limit, because you still have the mystery of the Kuiper Cliff, where something seems to be shepherding it, and maybe there's a planet 11 out there, or further. But there is no shortage of Kuiper Belt objects. You could go to Quasar, one of those, and get materials. But I think that we might be in a situation below a certain mass where we could dramatically extend the amount of known Kuiper Belt objects through the Vera Rubin Observatory. What are your views on that? Do you think there's a lot more in the Kuiper Belt that we haven't discovered?
Oh, for sure. Yeah, I think the Kuiper Belt is so... I mean, you think about the explosion of discovery that has happened since basically the invention of CCDs in terms of astronomy, and the two huge explosions that come to my mind: the discovery of exoplanets, which were certainly enabled by CCDs, and discovering these tiny dimmings in starlight thanks to their incredible sensitivity. But at the same time, that greater quantum efficiency of those chips compared to photographic plates has enabled us to be able to find objects which were beyond view until sort of the late 20th century. And so, if you look at the number of detections, it's been exponential in both exoplanets and in the outer solar system, these TNOs mostly. But the going further, obviously Vera Rubin is going to really make huge inroads in that, and I think it's incredibly exciting to see exactly what it's going to find. I know one of my students, Ben Cassess, has been trying to push the envelope with what you can do even with TESS, because TESS is also an all-sky survey, and it's certainly not designed to find objects in the outer solar system, because it doesn't stare at the same patch of the sky too long, and it takes fairly long exposures. But you can actually sort of back engineer the images, do this kind of, they call it like a moving stack. So if, it's kind of the same thing with any asteroid. Is obviously, if you take a bunch of images, it's in a different place. The problem with normally stacking images, which is what astronomers do all the time, if you stack images, it increases your signal to noise by the square root of the number of images that you stack. So very advantageous. But for an asteroid or a comet or something, you can't do that because it's moving. So you have to be able to detect it in a single image. And so they've pioneered this method, Melina Rice and Ben Cassess, of where you do a kind of iterative shift stack. So you essentially guess a possible orbit for an object. So you just propose one. You say, I'm going to guess there is an object which is following a certain Keplerian orbit. You know it's going to be a Keplerian orbit, and you know it's probably going to be close to the ecliptic, because that's where a lot of these objects live. And so you propose such an orbit, and then you take the images and you imagine there was an object in each of those images, and you stack them such that they would phase align. And then you check in that stack of all those test images, do you actually see a detection or not? And they actually have recovered several objects. And I think they actually got one new detection out there as well. They were looking for Planet 9, and they weren't able to find Planet 9, of course, like so many other people who've been trying to find Planet 9. But they're able to get some, impressive upper limits out of the test data. But I think that idea of phase stacking data is so clever, and that's going to take Vera Rubin to another new level, right? So I think already as you said, like 3i Atlas is very impressive, that even in engineering data, just in a single image from Rubin, you can see it quite clearly. But imagine what you could do if you could extend Rubin's reach even deeper by doing, kind of this co-addition of images. You'd be able to really dig down into the outer solar system and find some cool stuff. So both, that's just to say it's not only the hardware that's improving. Still today, software methods are making great strides, and there's new ideas. I mean, I think, as we talked about with T.A.R.S, but also here with this software stacking, it's really easy to think that all the good ideas have been had, right? And that there's I don't want to get into astronomy or physics because everyone's thought of everything. It's all been done. And it couldn't be further from the truth. You just can't believe, John, how much simple stuff, low-hanging fruit is left there for people to figure out. And this is just a really great example of that. So hopefully, if nothing else, these conversations inspire people who are sat on the fence about what they want to do with their lives, that if you have good ideas, like we desperately need those good ideas in this field. There's only 10,000 professional astronomers, I think, on planet Earth. And there's certainly more Kuiper Belt objects than that out there. So you could have personally probably 1,000 Kuiper Belt objects to yourself to study for the rest of your life, let alone the exoplanets and stars and galaxies.
Yeah, and nothing says that you couldn't have an ice shell Kuiper Belt object. You get enough radioactive decay going in the core and maybe maintaining some water. So they're on, maybe marginally, but they're on the list of potentially habitable ice shelves. So you have that idea that maybe there's something far out there, and it'll take us thousands of years to drill into every single one. But also with low-hanging fruit and that, I mean, well, look at your idea with the telescope. I mean, we haven't done that yet, but we could. And the idea of being able to resolve, exoplanets, distant exoplanets, brings the universe to you, so to speak.
Yeah.
And so you don't have to go out there. You can spend generations sending out your microprobes because you're collecting new data that you haven't seen before from the comfort of home. Let me ask you this. Can you turn a TARS into a telescope? And somehow come up with some idea on how to put it out at the distance you would need for a telescope? Is that have I gone too far? Have I gone too crazy into sci-fi speculation here?
Well, certainly the fact it is spinning so rapidly as an optical telescope would not be ideal. However, when you think about it as a magnetic field device, then it could be potentially interesting for measuring electric fields in space and measuring solar activity and things like this. So it might not be a telescope in the conventional sense, but perhaps there is some ways it could be used to sense other non-optical aspects of electromagnetic radiation. Kind of a wild, bizarre thing about this is that if an alien civilization could build a very massive TARS, that would be a gravitational wave machine as well. So anything that spins like this, just like think about a binary neutron star that's spinning, and as it coalesces, that produces all these intense gravitational waves that we can detect with LIGO from, millions of light years away. And we can actually make, just spin your arm around your head and you are making gravitational waves. They're just very, very, very small. If you wanted to produce a more meaningful gravitational wave, you could get a whole bunch of people to spin their arms in exactly the same speed at exactly the same phase as each other. And those would co-add coherently to produce a more intense gravitational wave. And so if you did that with these massive spinning objects and they were sufficiently massive, then you could, in principle, produce artificial gravitational waves with a whole fleet of TARS as well. So, that's certainly not something I was proposing in my paper, but it is fun to think about how other civilizations might exploit these physical principles, because the universe is a game, right? It's like just finding the hack codes. It's just finding the cheat codes that are embedded within this world that we live in to try and do whatever you want. And it's kind of wild when you work through the physics that there's no reason why these things can't happen. Right? There's no physical principle that stops us from doing any of these things that we've talked about. And it's like we're playing the universe in sandbox mode. And that just gets me so excited, as a physicist, that we have agency, right? There's these rules, and in one sense they seem limiting, like the speed of light seems slow and we can't just create magical forces out of nothing. There's these strict limits of forces we can use, but if you really put your mind to it, there's actually a huge amount you can do with these limited tools that we do have. So I get excited about that. And I would just say for the telescope aspect, this is obviously using an atmosphere to lens a signal. And maybe we'll talk about this a little bit, but there was a recent suggestion by Avi Loeb to use Juno to catch up with 3i Atlas. And of course, it doesn't have enough fuel to do that, as it turns out. But I've been prodding Juno for a while to do something else, and that was to test the telescope, which would really be a Jupiter scope, in this case, a Jovoscope. If it's actually at the right orbital distance from Jupiter, that it's in the focal line, the atmospheric focal line. And so as it passes behind in the shadow of Jupiter, at least the shadow as perceived from the Earth's perspective, it could ping a radio signal. Now, normally that radio signal wouldn't reach us. It would just hit the back of Jupiter and that'd be the end of that. But because of the atmospheric lensing, it would actually get beamed towards us and become 50,000 times stronger, that signal, if the theory holds up, that is. And so this is a wonderful test of the Jovoscope and Terrascope ideas. All it would have to do is just slightly adjust the orbit, and I believe it has enough fuel to get into that orbit, but I haven't done the detailed calculations, but I suspect it's not a lot of fuel it needs to get into that position. Ping a radio signal, and then it would be able to be detected back on Earth with DSN, and you would just see that it's way, way louder than Juno should be able to produce a signal of, and that would essentially prove the concept. So I'd be excited if we could, if anyone's listening who's involved in Juno wants to write to me, I'd love to talk more about that.
Screaming Juno, I love it as proof of concept of
Screaming Juno.
Yeah, as proof of concept of the Jupiter telescope. I don't even know what you would call that, because I don't think there's an equivalent term for terrascope for a gas giant.
Yeah, and it's not even a scope; it's an antenna. Because basically every scope can be, it's an amplifier. Yeah, exactly.
It's like a gigantic Marshall half stack, where you all of a sudden Juno gets orders of magnitude brighter in radio.
Yeah.
And all right, so Juno is destined for plunging into Jupiter anyway, right? Like soon. I think at the end of this year.
Mm-hmm.
And I understand the reason why, because you don't want it to eventually hit an interesting moon and contaminate it, so you just plunge it in there. But like with Cassini, you remember they plunged that into Saturn, and it was able to take data all the way down. Do you think that's what they're looking to do with it? Do you think that they might say, well, we could try that, but then we still have a dead spacecraft out there, or maybe we should try to collect data, much closer to Jupiter just before it plunges in there? Do you think that they would do that sort of cost versus benefit analysis with this?
Yeah, I have zero involvement in the mission, so I really don't know. All I can say is that I certainly hope they do. The Jupiter atmosphere still has so many mysteries. It has been probed, obviously, thanks to the Juno mission, but not directly, mostly through sort of these different oscillation modes that we've been able to detect in Jupiter's atmosphere. But I think the actual sampling and probing and measuring even just measuring the telemetry closely as it falls in would give you a huge amount of information. So yeah, I don't know exactly what's possible with the communication limits and the power limits. And obviously Jupiter is an intense radiation environment. And so it may be that the spacecraft just can't survive. It has survived pretty well up to now, but there may be limits as to what it can sustain as it plunges in. So I think those are all really interesting questions. And hey, John, you should get a Juno team member on to talk about it, because I think that's a really interesting prospect.
Yeah, and also a retrospective of the mission. What all did it find?
Yeah.
Because I actually think Juno didn't really get the coverage that something like Voyager 2 did, because, we do it more often, been there, done that effect. But yeah, I might do that. Now, gravitational waves and the Fermi paradox. Yes, I've got it looming, as I always do. So it's been suggested that a better way of signaling, because you have no noise, gravitational waves just propagate at the speed of light, meaning that it might be better for messaging than radio, long distance. So if you have aliens that have a bunch of giant T.A.R.S sending out gravitational waves, I don't think we have the sensitivity right now with gravitational wave detection to see something like that. But say you did, say you had a space-based receiver system of sorts, multiple probes receiving and measuring the gravitational waves propagating through. Could that be a solution for the Fermi paradox? Is that it actually turns out it's much easier to communicate with gravitational waves than we thought, and that's what aliens do long distance, and they don't emit strong radio, and that we're just simply completely blind to them right now because they're using T.A.R.S systems to communicate.
Yeah. I mean, I guess the problem with very broadly, with any Fermi paradox solution, you always run into the monocultural fallacy problem, as Jason Wright likes to talk about. So it's difficult. You can maybe convince yourself that some civilizations out there, advanced civilizations, indeed doing as you suggest, they're using gravitational waves, and there are certainly advantages to doing so. One clear one in my mind is that the signal drops off as 1 over distance rather than 1 over distance squared. So that's huge. That's why we're able to detect black holes merging so far away in other clusters of galaxies. I mean, that's crazy. The scale of the universe we can probe with that thing. In fact, one of the successors to LIGO, I think it's called the Big Bang Observatory, will be so sensitive it will be able to detect every black hole merger within the particle horizon of the universe. There won't be a single black hole merger that could occur that we will not be able to detect in the entire universe. That's insane. And we can do that with basically existing technology. That's how ridiculously efficient the transmission of gravitational waves is. So that's a really clear benefit. But there's a huge downside to it, and that's the challenge of actually producing such a signal. Yes, you could use TARS, but you would need very massive systems to do that. I mean, detecting black holes merging is one thing, but even I think, pushing for those future generations of LIGO, they're not sensitive to, say, a planet merging into a star. So as a planet spirals in, which is happening for several hot Jupiters, as they spiral in, people have actually done the calculation of, well, that should produce a gravitational wave. Could LIGO detect that? And all of those signals for both LISA and LIGO, I believe, are too small for us to be able to detect. So that just goes to show you that even if you have a Jupiter-sized piece of mass in space, even that our current systems can't detect. So that kind of maybe pours a little bit of cold water on it, that if you really wanted to build a transmitter, you're going to have to be able to control stars almost at this point to make it at least something that we could detect with current technology. But maybe they have some way more sensitive gravitational wave detectors than we do. And then you quickly run into problems that, okay, now you not only need a very impressive antenna, but you also need super, super LIGO detectors. So anyone who could build that kind of stuff presumably could also build a radio transmitter and receiver, which seems a lot simpler to build than one of these gravitational wave machines. But even if, and then on top of that, maybe you can imagine some civilizations, despite all of those problems, still go ahead and build gravitational wave detectors and receivers. But it's hard to believe that everyone in the universe would come to the same conclusion, because as far as we can tell, it's definitely not a slam dunk case that gravitational waves would be the obviously superior way of communicating. And so, yeah, I think to me, the problem is you'd expect there to be, at the very minimum, civilizations going through a phase of using radio, and we don't see any obvious radio waves in the universe. And second, there'd probably be a subset of even advanced civilizations that continue to use radio because it is just so damn cheap. If you care about economy and costs of building things, then you probably will always want to lower your costs, and radio has a lot of advantages as well. So, yeah, I could understand. I would certainly be comfortable if someone wrote a science fiction story, John, maybe it would be you, who, where gravitational wave machines are being used for communication. I would see that as totally plausible. I think the notion that everyone in the universe exclusively uses that is a little bit of a harder pill to swallow.
Well, I sort of juxtapose it against the ideas early on in SETI, like Coney and Morrison, where they were envisioning beacons, omnidirectional beacons just blasting out radio energy. And I'm like, well, what if they tend to stay radio quiet as we do, because we're not very detectable, but at distance because of inverse square. So you lose strength with distance, and you also, run into opaqueness. Light gets absorbed, and there's a lot of stuff, especially in like the galactic plane, that can absorb everything. I mean, we can't even see the other side of the galaxy because there's a giant dust cloud in the way. So it seems to me that there might be advantages there a long distance, but you can't actually detect the radio if they're still producing it because it's just weak. And when you're looking at like microprobes, like with TARS, those signals aren't going to be very loud. You're not going to really be able to eavesdrop in on the human transmissions coming from the microprobes from 10 light years away or 100 light years. You're not going to see it. So this could be going on right now everywhere, and we just simply, it's too weak. It's too weak. You would need a radio telescope the size of New York City, right, to start looking for a lot of signals. In other words, humanity from a distance of 10 light years, other than certain tricks, like when Arecibo was radaring asteroids, it produced a pretty radio loud signal, but usually we don't do that. So I wonder, maybe the loud civilizations are doing it in gravitational waves somehow.
Yeah, I mean, and equally you can wonder about other forms as well, like neutrinos, for instance, have certain advantages over optical light for the same reason. Like neutrinos will pass straight through the sun, so similarly, like there can be a huge amount of stuff blocking the way, but neutrinos will just tunnel through planets, tunnel through stars, and still get to their destination. So the problem is we don't have a detector which is very efficient at receiving them right now. But if you could crack that, then there would be obvious advantages. Yeah, there is a fun idea of using particle accelerators. You can sort of deliberately change the path of the circuits to maximize the neutrino beam that would come off them. And I think I did a video about this a while back. If you make that beam intense enough, you can actually trigger nuclear fission in a dormant warhead. In like, let's say there was an adversary on the other side of the planet, you can send your neutrino beam straight through the planet, and there's nothing they will be able to do about it. And you'd be able to focus that beam on the fissile material, and you'd be able to induce fission and basically cause it wouldn't be a full blown reaction, but it would be still a lot of energy it would dissipate, and it would certainly destroy whatever container it's in, but it wouldn't be a full Hiroshima type nuclear chain reaction. But yeah, neutrinos, like whenever you get into a different form of energy, neutrinos or gravitational waves, you realize there's all these like wild stuff that no one's thought about, and all this potential for it. So yeah, if in a three-body problem, maybe that'd be the most obvious, in the story, that would be the most obvious one trick that an alien civilization could do, right? They could target a neutrino beam straight at the Earth and just trigger all of our nuclear devices to be disarmed. And there'd be like very little we could do about it.
So there is an elephant in the room in the universe related to this that we know basically nothing about. So the neutrino is a weakly interacting massive particle, and maybe a form of dark matter in itself. It's just not enough to account for dark matter. But if there,
it is for sure. It is dark matter.
It is dark matter. It's proof of concept for dark matter. The thing is that we talk about neutrino communications, but what beasties lay within dark matter itself as far as communication? And that is the solution of the Fermi paradox, is that they're using an unknown particle to communicate that we can't even detect other than its gravity. So,
I still think that's kind of similar to the gravitational wave problem I would have, that it'd be, because that sort of implies that, the nature of dark matter is that it doesn't, as far as we can tell, interact with anything except for gravity. It's extremely weakly interacting. And so if you're going to use that as a communication system, you need to be able to produce it, which we don't know how to do that yet, but maybe you can figure that out. But more importantly, you need to be able to detect it. And we have built huge detectors under the ground in these mines, and we've been looking for this thing in particle accelerators for decades, and we cannot see any hint of this particle. It is extremely weakly interacting with ordinary electromagnetic radiation. And so it would be, unless there's something we're totally missing, it's difficult to imagine it would be a natural choice for a communication system. And Sagan used to always say that like radio is hard to beat, right? Because it's so cheap and easy to produce, and it literally travels at the speed of light across the universe. So I appreciate there are some disadvantages in terms of it will interact with dust and things like this, but all of that you can actually mitigate by choice of frequency and by sort of the directionality of your system, and thinking about shelling points and sort of ways of optimizing the receiver. So that's I still think there's a problem there, that it wouldn't be satisfying to me as a solution to the Fermi paradox to say everyone just uses dark matter, because it still is strange that nobody would use radio, because it just has so many obvious advantages.
I think that with radio comes in the efficiency question, because if you're an alien civilization out in the Milky Way and you've got decent astronomy, and you know that there is, you found Earth, you observe it, and you know that it probably has a biosphere based on the gas disequilibriums, but you know nothing about anything other than it has weird gases. And if you're at any distance, any real distance, other than very, very close, you're not going to see our radio, you're not going to see our freon in the atmosphere, you're not going to see any of that. You're going to see Earth in a much earlier state. So there may simply be no incentive to point a radio signal at us. They're like, well, what's the use of spending the energy to send a signal to a planet that very likely is just loaded with algae and dinosaurs, and that there's simply, you have to wait. And that the the simple solution to the paradox is that no one's pointing a signal at us that we could detect, and it just maybe they do every million years.
That's true, but
for a time, and see if there's anything going on. But we may be in the time where they're not doing that, or no one's doing that. Even if there are 10,000 alien civilizations all doing SETI experiments, there just may not be enough time for them to know that there's anyone here to contact. Who wants to try and spend enormous amounts of energy to send a radio signal to a fish?
yeah,
You wouldn't do
I
it.
could flip that around though, and I've been thinking about this for a little while. There's so much about the Earth. I'm by no means a rare Earth proponent, but I mean, it is possible that is the case, and there is certainly a lot about the solar system in terms of its structure, its architecture. Just even having a Jupiter-sized planet is unusual. Our sun is very quiescent compared to other stars. It's a yellow star. That's unusual. We're not in a binary star system. That's unusual. And even having an Earth-like planet is clearly unusual. We've learned that from exoplanet surveys. So there's just a lot of stuff about our solar system that's odd. And I think it would also be odd in time, right? We're a mature biological planet. So let's say you were another civilization with the capabilities of like the HWO, the Habitable Worlds Observatory. You'd probably be able to probe the Earth and tell, okay, let's say 1 billion years ago you had HWO. You'd be able to tell the Earth had multicellular life on it, or starting to emerge. Multicellular life was about 600 million years ago on the Earth. So you'd know that the Earth was at an advanced stage of biological activity, even if there wasn't intelligent life on it. And I think that would also make it rare. I mean, certainly in the solar system, it's obviously rare. Amongst the 9 planets in the solar system, or 8 planets in the solar system, it's certainly rare. But I suspect it's rare even beyond that. And with the time aspect, it makes me think it could be even quite extreme. And so I just think it's kind of odd that, as a tourist destination, Earth is perfect. I would claim, right? We are a civilization which is going through the most challenging point of our evolution in many aspects as a society, right? There's so much happening right now on our planet, and developments that are happening in terms of coming into terms with our own technological capabilities capable of destroying us, the transition to maybe intelligences that are more advanced than our own, and these capabilities of even creating life from scratch. Like there's an awful lot that is happening on this planet that is pretty damn interesting, I would say, if you're an anthropologist, an alien anthropologist. And so it kind of surprises me that the Earth doesn't get more attention. I think if you're going to pick a random planet, sure, there's 100 billion planets, but I think the Earth is not a random planet. I think if you're an alien civilization, you would know this planet is very, very high on my list of interesting planets to be looking at. And I just kind of question then, either we are, I think the zoo hypothesis actually looks, quite attractive in that sense. One option is that they are just interested in staying away from us and seeing if what's going to happen. We're like a historical experiment of maybe their own past, of something they went through. Or there's just no one out there, and they're really not there's no one to communicate with, because there's no one out there to communicate with in the first place. That's possibly the even simpler explanation, and by Occam's razor, I often tend to lean towards simpler explanations. So for me, that is a real puzzle. I think there are certain benign things about the solar system, but I think when you stack up a lot of these coincidences, you can also make a strong case that the Earth would be a super interesting place for another civilization to be looking at.
You would think, but my own feeling on the Fermi paradox is along these lines, that intelligence is simply very rare. It very rarely gets here because Earth only got there once, and it took how long? And that to me seems to provide a very simple answer, that civilizations are just very distant from each other, which reduces their detectability to each other dramatically, and that maybe they could signal you with radio, but it's not worth it. They realize that intelligence is very rare and rarely coexists with another intelligence close enough to actually establish contact with it. And then you run into the physics problems of the time problem and all that. And it's like, there's a lot of hard steps there.
Yeah.
I don't like the idea of unique Earth. Let's put it that way, that Earth is the only one. I don't think that statistically you can really, with sheer numbers involved, I don't think you could say that. Mm-hmm. But what you might be able to say, and you might be able to back up, is that they're in another galaxy, and thus we can't see them. And even if they're 1 billion years old of a civilization, If they're distant enough, you wouldn't see them yet.
Yeah.
So you have all of these compounding problems that just say intelligence is rare. And that's why I focus on my microbes, because I don't think they're rare. I think that abiogenesis may have a simple answer as well, and that it's simpler than we thought. And that's kind of being borne out by recent research that, yeah, maybe we were overthinking that, and that things like cell walls, or not cell walls, but membranes that start looking like protocells forming on meteorite material is a recent one. You know, when it lands on Earth and gets the ingredients, it's got the soap, so to speak, to make these protocell-like structures. And also hot springs, it can seem to be able to do it. So there seems to be multiple ways to create a protocell.
Yeah.
Well, that's a lot simpler than they used to believe. And RNA generation seems to be a lot simpler than what we were assuming. You know, you don't need a radioactive beach to form it. So you just need volcanic glasses with nutrients percolating through, apparently. So there's all these things that say that it might be that microbial life is common and the universe teems with that kind of life, but it rarely reaches intelligence. It's my gut feeling.
Yeah, I would be comfortable with your solution. Yeah, I think I kind of would class that almost as like a soft "we are alone" type situation, right? It's like, it's not like hard the Earth is unique and hard that intelligence is unique, but effectively, in terms of the actual accessible space, we are alone. Effectively, practically speaking, we are alone is maybe a better way of saying it. And so, you know, one solution I kind of have a particular fondness for is that intelligence, maybe pops up once per galaxy or so, and that's about it. That would certainly be very consistent with everything we know about our own galaxy and the radio silence, and not just radio silence, but the lack of engineered stars and the lack of spaceships flying through the solar system and all this kind of stuff. But I think an attractive solution would be that once per galaxy or rough of order of that, you do get a spark. And when those sparks come, maybe it's inevitable that, you know, some fraction of the time they go through a transition that maybe we might forecast, some are forecasting for humanity, where you transition to AI and you transition to maybe machines and maybe a colonization phase in the future. And so that's why I really love the idea of doing extragalactic SETI, right? Because we necessarily can't live in a galaxy where that procedure has already completed. Because if you live in a galaxy like that is essentially impossible, because every single planet or the large fraction of the planets have been converted into computer substrate at that point or something, right? This colonization phase has played out. So there's no natural habitable planets left. And so we can't be born in such galaxies, but it is possible that the vast, vast majority of galaxies look like that. We just don't know. We haven't really done sufficient extragalactic SETI to be able to tell. And the reason why we live, even though it seems improbable what I'm saying, but it would be necessary. If that were true, we would necessarily have to live in the rare fraction of galaxies where we were the first. You'd have to be the first. Otherwise, if you were second or third, your span, the span is millions of years difference or whatever between each one, then you wouldn't be there to begin with. So that's why I'm a big proponent of trying to do more extragalactic SETI, because those are like separate petri dishes. They are decoupled from us. Our fate is not intertwined with what happens in those galaxies, unless, maybe you can believe they can warp drive across the universe or something. But if you put that aside, they're self-contained silos. And so what happens there is a fair and representative experiment of what happens in the universe in general.
Well, I'm trying to think of what extragalactic SETI you could do. Now, there's the idea of red spirals, where a galaxy-spanning civilization kicks out all the dangerous stars, and naturally the galaxy reddens. But that's one of the few that anybody seems to have thought of that we could look for, as basically a galaxy encased where all the stars are encased in Dyson spheres, and you see it in infrared, but you don't see it anywhere else. Yeah. But there are very few ideas. What other ones do you know about as far as looking for evidence of civilizations in other galaxies? And another elephant in the room is Andromeda, because that's close enough to where you could do some pretty effective searching, I think, if you can get there, or the Magellanic Clouds.
Yeah, well, I think when we talk about extragalactic SETI and you're talking about looking for galactic, not necessarily you're talking about looking for galactic scale phenomena, right? Things that span an entire galaxy. And so they're necessarily, you're also extremely advanced compared to anything that we could pull off. And so it gets very speculative as to exactly what their behavior and activity would be at that point. Certainly the Dyson sphere argument is not unreasonable. It's leaning on sort of the principles of thermodynamics, essentially, and just saying they're going to use energy to do something. We don't even know what they're going to do with it, but they will do something with it and that will produce waste energy. But it doesn't necessarily have to come out, thermodynamically, it doesn't have to come out as heat. It could come out as neutrinos. It could come out as gravitational waves. The energy has to be conserved, but it can come out in some other way than maybe just necessarily electromagnetic radiation. And so I think more broadly, when we think about very advanced civilizations, we tend to think more about anomaly detection. So, just use all the tools that we have, like you monitor it in every way that we know how to, and ask amongst the sample that we see, or at least compared to the Milky Way, maybe, what aspects of this galaxy are typical versus highly irregular. And so that's something I'm kind of excited about. I mean, me and my student, we've been working on a fun idea about star lifting, for instance, where you engineer stars to live longer. This is work with Matt Scoggins, and we did a video and a paper about this. I can't remember if I spoke to you about it, John, in the past, but we have a follow-up paper that we're working on this at the moment. So maybe I'll come back and talk about that one day. And we think that there will be a very clear and actually surprisingly detectable signature of star-lifted stars with just colors, just literally looking at the colors of the star and basic kind of HR diagram type stuff of where stars should live in sort of their evolutionary space, that they will stand out as clearly anomalous. And if a civilization has been living in a galaxy, especially an old galaxy, they may well have gone around taking all of the F-type stars, which have fairly short lives, and engineering them to live longer, essentially stripping mass off them so they look more like G-type stars and K-type stars, or maybe even M-dwarfs. And by that mass stripping procedure, you would see very clearly this galaxy has a complete paucity of high mass stars. What's going on? This doesn't make any sense. All of the colors are out of whack. So you would see an anomaly. So that's just an example of a type of behavior they could do. But I would just advocate more generally that we should just look for stuff that's really weird about galaxies and then try to dig down. And if you do that, it does have a downside that you're trying to, you don't know exactly what you're looking for when you start out, and has certain pitfalls. But on the positive side, if you find something really weird, that's interesting either way, whether it's truly aliens or whether it's just new astrophysics. Either way, it's going to be exciting to study those objects in greater detail. So I'd like to see Extragalactic SETI sort of lean more in that direction.
Yeah, just have a bit piggyback on galactic research in general, because there are still a lot of mysteries, and James Webb has gloriously increased the amount of mysteries regarding galaxies and their formation. We're studying them anyway, taking the data, maybe that, something can be teased out.
Yeah.
Now, I wanted to ask you this. Now, Interstellar is also one of my favorite sci-fi movies. I think it's one of the best ever made, except obviously for scientific faux pas. Matt Damon on a whatever those were, not a planet. Although I think my favorite is the ocean world on Gargantua wouldn't actually do that gravitationally.
Yeah.
But it is where it wins is drama and what it presents and the overall feel of the movie, which incidentally, there's actually a game called Deliver Us the Moon that captures that same feel. It's a very interesting game. What was it about the movie Interstellar that helped you into thinking enough about this idea to name it T.A.R.S?
Well, what I love about the movie is it has sort of a rebellious nature against the slow decline of civilization, right? So the Earth is going through a difficult period, and there's all these, there's these dust storms, which are sort of an allegory essentially for climate change, and there's even a science denialism which has taken a hold, right? And there's that famous scene where he's meeting the teacher, and the teacher denies the existence of the Apollo program and all these the humans landed on the moon. And so, that terrifies me, the prospect of us receding from our peak. And it's my other favorite, well, my absolute favorite literature, as fans might know from my videos, is J.R.R. Tolkien. And a continuous theme in all of his writing is decline, right? Just there's a certain peak, and it's really hard for civilizations to recapture that peak. And there's a gradual decline of beautiful things and of magic, essentially, in that universe. And so I love the rebellious nature of the characters to use the poem Rage Against the Dying of the Light, right? To fight back and to try and persist and to advance humanity even when few will try. So I was certainly inspired by the spirit of that movie. And I think the physics of that docking scene were just incredible. That I think that was really well done, very inspiring. And watching that with my kids and stuff, we obviously they weren't around when the movie first came out, but I've showed them many times since. It's just something we all love and get into. So I love the peril of if you do nothing, because when has the option of that ship that the Matt Damon's character has just basically blown up half the ship. There's an option of just by default of doing nothing and just accepting the decline and the loss. But then there's the resistance of agency, of grabbing the own agency in your life and doing something that people think is not possible. In that case, it is. Is it T.A.R.S, I think, that actually says it's not possible? He says no, it's necessary. I just love that audacity to try. And I felt that with this paper, that it's easy to think, and I mentioned this in the video, that someone else is going to come along and solve interstellar travel. And we hope that. I've certainly hoped that my whole life, that some genius will come along and present to me a warp drive, or will present to me a portal to another world, or a teleportation machine, whatever it is. And I'm 40 years old last year, and I started I didn't have quite a midlife crisis, but I was certainly starting to reevaluate my expectations for the rest of my life. And it started to dawn on me that I'm probably not, the way things are going, it's not looking very likely there's going to be an interstellar mission in my lifetime. And that just deeply saddened me. But I realized that, I might not be a genius, I might not be the next Albert Einstein, but hey, I've got agency. I can still choose what I do with my life, and I'm going to choose to try. And maybe I'll fail. That's the most likely outcome in any situation where you put your neck out there. But if we don't try, we're guaranteed. Of course, we're guaranteed to fail. So I felt compelled that I wouldn't be satisfied with the way my life is going unless I tried. And I would rather regret the things that I did and the things I didn't do at the end of the day. Like, I'd rather finish my career and say, okay, maybe I didn't solve all these things I wished I could solve, but I gave it my damned hardest. I really did try. You can't say I was scared of trying. And so that's why I ultimately decided to pursue this project and put my heart into it.
Yeah, and that's why I'm so obsessed with the microbes, because I am half a century old. And I wouldn't call it a midlife crisis. I'm a little bit past that. But the funny thing is that I didn't start as a YouTuber until after 40. So it's
life begins at 40.
Life begins at 40. But the thing is that I think we have a very solid chance of cracking abiogenesis and knowing whether it's very unlikely for microbes to exist very often in the universe, or it's very common. I think we have a way to tell within the next 20 years just through the abiogenesis experiments, people looking into that. Or we drill into Europa and there it is. Find something at Mars. So that's what I focus on is not the question of are we alone, because I don't think we can do that within my lifetime, but I think we might be able to say, is Earth life alone? And you get to tell the microbes you are not alone, something like that.
Yeah.
And that's what I see. But as far as interstellar travel, yeah, you have to start thinking about it, and that's what you're doing. And novel ideas like T.A.R.S advance that, because it gives us a completely separate way than Breakthrough Starshot, envisioning on how we could send something out and eventually get there. And I think it's amazing. Now, they're inevitably, given the times with 3i Atlas cooking through, there are always going to be those people in the audience that say, well, they're already here, in the form of UFOs, or which is jumping to a conclusion in my view, or an interstellar comet, like what 3i Atlas to me really seems to just be a very ancient comet, which is where my interest is. I'm like, that thing's really old based on the evidence we have. I want to see what it's made out of. But there is that answer. Now, do you think, and I'll frame this broadly, do you think that it is a fruitful way to think that maybe they are here and we're not recognizing it?
Yes, I think so. It's, I think one of my colleagues, I think it was Jacob Hack Misra, wrote about this in, I think it was Scientific American. He had a beautiful article. He talked about this, where he said many of us are compelled to try and look for alien life. And we conduct these activities like SETI and looking for technosignatures more broadly. And typically that activity is looking at other stars, but we're not unwilling to look between stars as well. I mean, like the WOW signal, for instance, initially appeared to be coming from between stars. And so people were speculating that it could be a ship or something that was traveling. And so similarly, we wouldn't be opposed to looking for life on Proxima Centauri, the nearest star. And yet it's weird that as this distance gets closer and closer, we start to become less and less comfortable with the science of it. And once it crosses the atmosphere, a lot of astronomers would throw it out and say, that's no longer scientifically credible to look for alien life in the atmosphere. But of course, that doesn't really, there's nothing special about the limit of the atmosphere. There's no reason why an alien that's floating just above the atmosphere is credible astronomy. And as soon as it dips 1 meter below, it's no longer credible astronomy. So I think it's certainly important that we keep an open mind and look for things which are in our skies and in our solar system. And as you know, I'm very receptive to the motivating argument behind it. As I alluded to earlier, I do think there's a lot, you can make a very strong case that the Earth has things about it which would be of exceptional interest, namely our own development, especially to another civilization. I don't think they'd be interested in our water. I don't think they're interested in our carbon because these elements are everywhere across the universe. But I think the most interesting thing about the Earth is what's happening with us and our development. And so I can understand the appeal of that argument. You do have the problem of light travel time effects, like how would they know that we're at this stage, et cetera, et cetera. But there's ways around that. You could have maybe a chain of, like these daisy chains we talked about earlier, of continuous monitoring. They might have been monitoring us for 1 billion years already at this point. So I certainly think it's interesting to try and do. I don't see any clear evidence of it anywhere. It's kind of always surprising to me that of all the people I know who, many, many professional astronomers and many amateur astronomers, and none of us have seen a UFO. And, we look at the sky a lot. I have a telescope in my own backyard. I'm observing every time there's a clear night. I've never seen anything. And that's a little bit odd to me that the people who are professionally trained to look up at the sky and are doing it more than most don't see any evidence of these visitations that other people claim. So that immediately is a bit of a red flag to the credibility of the idea that this is actually happening. But I'm certainly receptive to the argument that it could be happening. But if it was happening, we wouldn't detect it at all, right? Because if they were sufficiently advanced, they'd be hiding from us. What's the point of doing an anthropology experiment if you interfere with the experiment? You don't want to interfere with us. So you would make sure that you would not be detectable to us. And you can imagine very advanced technologies, cloaking systems, which could, make it impossible for us to ever see them. So in that case, if they're sufficiently advanced that they're undetectable, then you've got, kind of like, I like to use this analogy of Sagan's dragon, like an invisible dragon that Sagan used to imagine he had a pet in a demon-haunted world. It's undetectable. If it's completely undetectable, then it's not science. Like we just can't use the tools of science to look for that. So if you want to make the claim there are completely undetectable aliens hiding from us, fine, you can make that claim, but that's purely a position of faith at that point. There's no scientific evidential or experiment or test I can do to verify your claim. If you want to make the claim there's artifacts in the solar system, maybe relics, to me that's more interesting because those would be, malfunctioning or, defunct pieces of equipment that were left on maybe the moon or in orbit of Jupiter or something. That's more interesting because that's something that now we could use the tools of science to actually look for and put constraints on. And so I think it's something we should take seriously, but just make sure that we are cautious about casting it into a credible and well-framed scientific position. Right? We can't just have it's God of the gaps. It's just every weird thing we see, that's aliens, that's aliens, that's aliens. We have to design experiments to look for specific phenomena and then put constraints on those from those experiments.
Indeed, it must keep an open mind. And granted, I've seen some scientists that don't, but in this regard of close technosignatures, but you should look and you should throw ideas out there. And I certainly support that, but I haven't seen any evidence. I can tell you, though, I have had an anomaly, an astronomical anomaly over the last 2 weeks. I have seen 2 bolides.
Hey, lucky.
who just happened to be sitting outside. 2 outright bolides, and both of them were bright green. And they traveled, one of them traveled the entirety of the sky. And there's actually footage of that the entire Midwest saw that thing.
Yeah.
And then I go out and I see another one, 2 nights ago at about 5 in the morning, and I see another one, and it's also green. And I'm wondering, it's awfully close to the Perseid meteor shower. I'm sure they're sporadics, but seeing 2 like that, because I go, you see meteors all the time when you skywatch, but
Yeah.
bolides are different. You don't see that too often, and yet.
Lightning never strikes twice.
And it did. So go figure. I wonder. So I'm left wondering. They didn't have the speed of a Perseid. They were actually much slower. So they have to be sporadics, I'm sure. But could a comet shed a baseball-sized rock when passing through? Questions like that. Anyway, David, it's always a pleasure, and I look forward to the new paper. We'll do this again because starlifting, I don't think enough thought's been put into it. We've always had the concept, but actually doing it and things that worry me, like, all right, if you want to change the class of a star like the sun, you're going to have to get rid of that helium somehow, and things like that, questions like that. So when you release the next paper, I look forward to another conversation. Thanks again.
Yeah, sounds good.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.